Section: Introduction. In this section, we will discuss the advancements in large language models, LLMs, in recent years. These models have excelled in various tasks such as code generation, solving math problems, multilinguality, and more. However, training such LLMs demands significant computational resources and data, often involving thousands of GPUs and trillions of tokens. The traditional method of training involves maintaining multiple copies of the model on different GPUs and synchronizing them after each weight update. This frequent communication between GPUs poses a challenge in scaling the training to more GPUs and makes the process susceptible to hardware failures. To address these challenges, a method called Branch-Train-Merge (BTM) was introduced for parallel training of LLMs without synchronization to enhance pre-training efficiency. The BTM method starts by creating multiple copies of a base LLM and training each copy separately on different data subsets. This results in independent expert LLMs, each specializing in a specific data distribution like knowledge domains or languages. During testing, an input prompt is classified into relevant domains, and the final outputs are generated from the corresponding expert models to predict the next token. While the BTM method improves training efficiency, it lacks a unified single model, making further supervised fine-tuning or reinforcement learning challenging. Another approach to reduce the computational footprint of LLMs is the mixture of experts (MO) method, where only a subset of parameters are active at a time. This method has shown impressive performance on downstream tasks by allowing the total number of parameters to increase without additional computation. Our goal is to combine the strengths of BTM and MO while addressing their limitations. We achieve this by training multiple expert LLMs separately like in BTM and then combining them into a single model using an MO architecture. This combined model, called Branch-Train-MiX (BTX), merges the feed-forward sublayers of expert LLMs into a single MO module at each layer. A router network selects which expert to use for each token, and the model is fine-tuned on all combined data to learn to mix the expert feed-forward modules. The main advantage of BTX over MO is its embarrassingly parallel and asynchronous expert training, reducing communication costs and increasing training efficiency. Compared to BTM, the final BTX model is a unified neural network that can be fine-tuned or used like a standard LLM. BTX shows significant improvements over the seed model on various tasks, especially in math and code domains, outperforming BTM and offering a more compute-efficient and balanced performance across different tasks. Section Summary. In this section, we introduce the challenges of training large language models, LLMs, at scale, where synchronization during parallel training can lead to communication bottlenecks and vulnerability to hardware failures. To address these issues, the Branch-Train-Merge (BTM) method was proposed for embarrassingly parallel training of LLMs, creating independent expert models trained on different data subsets. We further enhance this approach by combining the benefits of BTM and mixture of experts (MO) methods, resulting in the Branch-Train-MiX (BTX) model, which offers asynchronous expert training, reduced communication costs, and the ability to be fine-tuned like a standard LLM, showcasing improved performance across various domains. Section: Mixture of experts. In this section, we explore the concept of mixture of experts, MO, and its application in scaling deep networks using a simple top-K routing scheme. When it comes to training models like the transformer architecture with discrete routing decisions that cannot be optimized through gradient descent, various training methods have been investigated. Surprisingly, it has been found that even a fixed routing scheme based on random mappings of input tokens can work effectively without any learning involved. In larger experiments involving recent large language models, LLMs, it has been demonstrated that the MO approach can achieve performance comparable to dense LLM counterparts while using a significantly smaller number of active parameters. Some studies have highlighted the benefits of having more specialized experts and incorporating a shared expert that remains active consistently. Our approach is related to continual learning as we train domain experts on datasets with different distributions compared to the initial training data for the seed model. This is achieved through continued training after branching, where experts in feed-forward layers specialize in specific domains using a domain-conditioned fixed routing method. However, our approach differs by incorporating asynchronous training. Moving on to the Branch-Train-MiX method, we aim to enhance the performance of an existing LLM that has been pre-trained on a broad range of topics in specific areas of expertise. This involves continued pre-training with corresponding training datasets related to specific knowledge domains such as math or code. The method consists of 3 stages: branch, train, and mix. During the branch and train stage, we initialize from the seed model and train multiple expert LLMs, each on a specific dataset related to a particular domain. This training process is embarrassingly parallel, allowing for efficient scaling in distributed training environments. After training, we end up with different LLMs specialized in specific distributions, which are then used in the subsequent merging stage. In the mix stage, we combine the domain expert models using a mixture of experts approach within each layer of a transformer. This involves merging feed-forward sublayers from different domain experts into a single Mo sublayer, where a routing function determines which expert to utilize for each input token. By efficiently selecting experts based on routing decisions, we can improve the overall performance of the model. Section Summary. In this section, we explore the mixture of experts, Mo, approach to enhance deep networks by utilizing a top K routing scheme. We find that even a fixed routing scheme based on random mappings can perform well without explicit training. By training domain experts on datasets with different distributions and continually refining them through our Branch-Train-MiX method, we can significantly improve the performance of large language models while efficiently utilizing a smaller number of active parameters. Section: Variations. In this section, we explored various modifications to our method. When it comes to load balancing, we tackled the issue of some experts not being utilized effectively in mixture of experts, Mo, models. To address this, we introduced a simple solution called load balancing. This method involves adding an extra loss term to encourage all the experts to be used equally during training. The loss term calculation involves the current data batch and a hyperparameter alpha. This additional loss is computed in each layer and combined with the negative log likelihood, NLL, loss. In terms of routing methods, apart from top K routing, we also tested other approaches. These include switch, a top 1 routing method, and soft routing, where all experts are activated using softmax during both training and inference. Additionally, we experimented with sample top 1 routing, which involves using the Gumbel softmax for routing. During training, we generate a soft sample and compute only one expert corresponding to the largest value, while at inference time, we perform hard sampling. We gradually adjust the temperature during training to reduce the gap between training and inference. To expand the number of modules in the Mo layer beyond the number of domains, we split each domain's feed-forward, FF, sublayer into multiple chunks. By splitting each FF layer into C chunks, where C is a specified number, we increase the total number of modules in the final Mo layer. Instead of initializing Mo experts directly from domain experts, we explored blending experts from all domains into each Mo expert. This approach aims to address the lack of domain specialization in Mo experts trained conventionally, by incorporating domain-specific information from each expert. Our experimental setup is based on the Llama 2 pre-training framework, using the Llama 2.7b model as our starting point. For BTX training, we utilize the pre-trained Llama 2.7b model and further train on domain-specific datasets to derive domain experts in math, code, and Wikipedia. These domain experts are combined with the generalist expert from the original Llama 2 model to create a unified Mo model. We then fine-tune this Mo model on all datasets used for training the individual experts and continue training for additional tokens. Various routing methods and load balancing techniques are applied during training, with specific parameters adjusted accordingly. Section Summary. In this section, we experimented with various modifications to our method, including load balancing to address dead experts in mixture of experts, MO, models. We explored different routing methods such as switch, soft routing, and sample top 1, and also discussed strategies for splitting and blending experts to enhance domain specialization. Our experimental setup was based on Llama 2 pre-training, where we utilized a seed model with 7B parameters and trained domain experts in math, code, and Wikipedia datasets, along with a generalist expert, to create a comprehensive MO model. Section: Baselines. In this section, we compare our method to several baselines. We start with Llama 2, where we use both the original 7B model and the 13B model. The dense baseline involves training the seed model with all the data instead of separate models for different domains. We also consider sparse upcycling, which initializes a MO model from the seed model with 4 identical copies of the feedforward module as experts. Another baseline is Branch-Train-Merge, BTM, which uses expert LLMs directly without a MO model. We also have Code Llama 7B, a code specializing language model, and Lemma 7B, a math specializing language model. For evaluation, we assess zero and few shot performance on various benchmarks testing math reasoning, code generation, world knowledge, reasoning, and general skills. We use the Atom W optimizer with specific settings and a batch size of 4M tokens and sequence length of 4096. We analyze how expert LLMs specialize in specific domains and find that they excel in their respective tasks. BTX improves tasks where experts specialize, as shown in aggregated performance results. Compared to other methods like DM, BTX shows better performance on average, especially in math and coding domains. It outperforms BTM significantly, indicating the benefits of MO fine-tuning. BTX is more compute efficient and robust to task interference, surpassing Llama 2 13B in most tasks. When compared to sparse upcycling, BTX trains with more data and achieves slightly higher average performance across all domains. Section Summary. In this section, we compare our method, BTX, with various baselines including Llama 2, dense, sparse upcycling, and BTM. BTX outperforms these baselines by improving performance across multiple domains without regressing on other tasks, showcasing its efficiency in continued pre-training and robustness to task interference. Additionally, BTX achieves better results compared to Llama 2 13B and sparse upcycling, demonstrating its effectiveness in utilizing training compute efficiently and achieving higher average performance across different domains. Section: Better compute performance trade-off. In this section, we compare our BTX model with baseline models in terms of compute efficiency. The x-axis in the plot shows the total training compute starting from the seed model, measured in GPU days, while the y-axis represents the overall performance. BTX outperforms dense and BTM models in terms of performance. Despite using a fraction of the total training budget during the MO training stage, BTX shows significant improvements in general capabilities compared to other pre-training approaches like multitask learning of the dense model and branch-train-merge. As a special case of BTX, sparse upcycling without expert training performs better than dense and BTM models but not as well as BTX when given the same or larger compute budget. The efficiency gains of BTX come from training the experts in parallel before MO fine-tuning. The MO models in BTX are similar in size to the Llama 2 13B model but use less than half of the additional training compute. This results in improved performance in expert domains such as math, code, and knowledge, leading to better overall performance. We also conduct ablations of the BTX training. Comparing different routing methods with varying numbers of active parameters for different amounts of fine-tuning, we find that the top 2 routing strikes a good balance between performance and efficiency. Additionally, freezing the feed-forward modules initialized from each expert and only training the rest of the MO model has little impact on performance across all tasks. In our routing analysis, we evaluate the performance of BTX on downstream tasks and examine the routing decisions among the experts. The top 2 routing with load balancing ensures a more uniform distribution of the load between experts, leading to improved performance. With load balancing, the code expert becomes more prominent in math and coding tasks, showing the importance of fair routing. Overall, tokens are often routed to the code and Llama 2.7b experts in math domain tasks, while the math expert is more relied upon in the math task. Load balancing improves coding tasks but may degrade math tasks due to changes in domain expert routing.